Our last example today, we'll do using the ideal gas law to figure out a molar mass. Now, with molar masses, we know that a molar mass is simply grams divided by moles. So we are told here initially, we've got that many grams, 0.281. What we need to figure out is the number of moles. So let's go ahead and write that down right now. We have 0.281 grams of the sample over some number of moles. Don't know it yet. But what we can do is, since we have a volume and a temperature and a pressure, we know 3 of our 4 parameters. We can use the ideal gas law to figure out the 4th. PV is equal to nRT. The pressure is 754 torr. The volume, 127 milliliters. We have to convert that to liters. So that'd be 0.127 liters. Got to divide by 1,000. N is what we're trying to find, the number of moles. R, since our value is torr, we need to use the 62.36 liters torr over moles Kelvin. Temperature, 98 degrees plus 273 is 371 Kelvin. To get moles by itself, we're going to have to divide both sides by the 62.36 liter torr per mole Kelvin and 371 Kelvin. When we do that, torr get canceled, liters get canceled, Kelvin get canceled. I have 1 over the reciprocal of moles, so I'm going to have moles as the unit. 754 times 0.127 divided by 62.36 divided by 371 to 3 sig figs. 4.14 times 10 to the negative 3rd moles. So that's what I'm going to put back into my original equation. Which means my molar mass the 3 significant figures would be 67.9 grams per mole. So there we have just a simple application of how we can use the ideal gas law to go beyond just those very simple kinds of problems where we just manipulate and figure out the missing variable. All right, taking that silence for no. Let's talk about another application of the ideal gas law. In this situation, we can talk about using the ideal gas law and standard temperature and pressure to figure out the density of a gas. The problem with these kinds of calculations, honestly told, I don't use them particularly much. It's very useful if you have that equation in hand at the moment. But if you have a simple understanding of the ideal gas law, we can manipulate it appropriately. Why this is important is buoyancy. By knowing the density of a gas, we can figure out where that gas is going to exist in our atmosphere. Lighter gases are going to exist higher in the atmosphere. More dense gases are going to exist lower in the atmosphere. That's why there's so much carbon dioxide and oxygen down here, because of the gases, they're considerably heavier than, say, your hydrogens and your heliums. Now, when it comes to something like a hot air balloon, well, that's actually something else at play. That's an application of Charles' law. When we heat up the air in a hot air balloon, we're not changing any of the gas, but we are expanding its volume. So the amount of gas doesn't change, but the volume does. So that means that the density is going to go down as a result. And we heat it. The more we heat it, the more it expands. The less dense it's going to be, the more that balloon can go up. So what we're looking at here then is this. Here's an example of a gas density problem. Now, with that equation that we just had, E is equal to the molar mass times the pressure over RT. If you know that equation, problems like this are pretty straightforward, because all that we need to do is just simply input the correct variables in the right places. And really the only thing that's stopping us here is we have a pressure in millibar, but we don't have an R value in millibar, so we would have to do that conversion. The conversion itself, not too terribly difficult. We just need a table of conversion values. With 1 atmosphere being equal to 1013.25 millibar, we could easily turn that into atmospheres and go about our business as we were before. So 1024 millibars with 1013.25 millibar in 1 atmosphere. The 4 significant figures, it's 1.011 atmospheres. So putting in the values, 28.8 grams per mole multiplied by 1.011 atmospheres divided by 0.08206 liter atmospheres per mole Kelvin, and 26 Celsius would be 299 Kelvin. So if I follow through here, atmospheres cancel, Kelvin cancel, 1 over moles cancel. All that is left is grams in the numerator and liters in the denominator. 28.8 times 1.011 divided by 0.08206 divided by 299 would give us three significant figures, 1.19 grams per liter. So like I said, if you have this equation, that's a very easy way to figure out gas density. If you don't, you can still go back to the ideal gas law. All that you need to do is manipulate the equation. And what I mean by that is, if this is our equation, PV is equal to nRT, what we can find is something like the molar density, where I can turn this into N over V is equal to P over RT. This would give me moles per liter. In a solution, we would call that molarity. Here, we're just going to call it moles per liter. All I have to do once I find that is multiply it by the molar mass, and it would turn the moles per liter into grams per liter. So if I follow that same process, I still have the same pressure, 1.011 atmospheres. The R value is still the same, 0.08206 liter atmospheres per mole Kelvin. Temperature still 299 Kelvin. If I do my crossing out, the atmospheres cancel, the Kelvin cancel. What I have at the end of this process is 0.0412 over liters per mole, which, if you remember from algebra, a reciprocal of a fraction just flips that fraction in the denominator. So 0.0412 moles per liter. And now if I multiply that by the molar mass, 28.8 grams per mole. The moles cancel, 0.04 times 12 times 28.8. I'm going to get to the same three significant figures, 1.19 grams per liter. So why go through all of this to show you this? Again, it comes down to your equation sheet doesn't have every single equation on it. So if you've memorized this density calculation with this formula, great, use it. It is simpler. But if you didn't, understand that this has its roots in the ideal gas law. And if you can use the ideal gas law to get a similar ratio, all that you have to do is convert that ratio of moles per liter into grams per liter by multiplying by the molar mass. That's all that I'm trying to show you here. The ideal gas law is versatile. You're going to find it useful anytime you have to do calculations involving moles.